I have a cylindrical piece of metal in my hands and I am going to feel its weight, and then I have a bucket of water and I am going to take this metal piece inside this bucket and feel its weight again. Clearly I noticed that there was a difference in weight. When I weighed it outside water, then it felt heavier to me as compared to when I did it inside the bucket. So that's something that the liquids do. They make things lighter, and that we are going to learn today in this video. I have taken a container just like the bucket, and inside this container there is that cylindrical metal piece. The base area of this metal piece is A, and the height of this metal piece is H. If I list out my forces on this metal piece exerted by the liquid, and this is some liquid which has density rho. In the video it was water, so we can assume that it is the density of water. And let's assume that the atmospheric pressure is P0. And from the top of this container, let's say this depth is T. So the force from the top on this metal cylinder will be this force. Let's say this is F top. So F top is going to be pressure at that point, which is P0 plus rho gt into the area, and the area of this is A into A. And the force from the bottom, Fb, will be force from the bottom will be pressure at the bottom, which is P0 plus rho g d plus h into the base area A. Now these are the forces due to the liquid on this metal piece. The net force due to the liquid, because I can see that this force Fb is little greater than this force Ft. So let's find out the net force, which will be in the upward direction. So the F net, which will be Fb minus Ft, will be this minus this. And if I subtract this, P0 would get cancelled out, and this rho gd part will also get cancelled out. So if I subtract, so this and this will be gone, and this part and this part will be gone. So what will remain will be just rho g h into A. This will be the expression of the net force exerted by the liquid on this. And now I can intuitively understand that yes, there was some force exerted by the liquid in the upward direction. So to balance its mg, I had to apply a little lesser force. In the previous case, when this was outside, then all the weight was falling on my hands. But in this case, there is some force in the upward direction which will reduce that weight. We'll make the free body diagram in a while, but let's confine our focus here. In this case, this rho g h into A is a very interesting quantity. Let's see what it is. Rho is the density of the liquid, not the density of the metal. So this quantity rho into HA is something interesting. This HA is the volume. That is the volume of the metal, or if you think from other perspective, this is also the volume of the liquid displaced. So this much volume which has been occupied by this metal piece was previously filled with water, but this guy has taken that place. So the volume displaced of water is V, and V into rho, which is density into volume, is the mass of that liquid displaced, into G is the weight of that liquid displaced. So this net force is weight of the liquid that is displaced by this metal piece. This is essentially Archimedes' principle. It states that if any body displaces some liquid, then there will be force acting on that body, and that force will be equal to weight of the liquid displaced. So this force is called buoyant force. Buoyant force. To understand Archimedes' principle better, I have taken two examples. Let's check them out. In the first example, there is a cubical iron block that has side 1 meter. So its volume is 1 meter cubed. Volume of this is 1 meter cubed. And it is submerged inside this water. and it is tied to a thread which is fastened to the top, as you can see. The question is, find out the tension in this cord. So you have to find out what is the tension in this cord. Density of iron is given 10,000 kg per meter cubed, density of water 1000 kg per meter cubed, and G is 10. If we draw the free body diagram of this iron piece, taking this as our system, and list out all the forces acting on this iron block. So there is one force that is downwards, which is mg on this block, and then there is buoyant force that we just saw, and then there will be tension. To find out the direction of tension, so if this string is cut, then this iron block is going to sink down. Therefore, this string is not letting this iron block go down, so it is going to pull it in the upward direction, which is our tension. Now the net of all the forces on this iron block is 0. So upward force, tension, plus Fb will be equal to the downward force, which is m into g. So tension will be equal to mass of the block. Mass of the block will be equal to density of iron into volume of iron into g, minus buoyant force will be, as we just saw earlier, will be the weight of the liquid displaced. So in this case, weight of the liquid displaced will be mass of the liquid that is displaced into g. Mass of the liquid displaced will be density of the liquid, that is water, into its volume, that is the same volume of the block, into g. And from here we can take Vg common, rho I minus rho W. This is our tension in general form. If we can substitute the values, so V, I just saw V as 1 meter cubed, and density of iron 10,000, density of water 1000. So we can substitute it here, 1 into 10 into 10,000 minus 1000. This is 9,900 into 10 will be 9,900 into one more 0, which will be 99,000 newtons. So 9.9 into 10 raised to the power 4 Newton. This is our tension, and this is the answer that is required. In one more case, as shown, in this situation is little bit different, in the sense that instead of iron, there is wood. Wood has lower density, 800 kg per meter cubed, and this has a tendency to come to the top. But this string here is holding this guy. And again, the question is to find out the tension in this string. So again, let's draw the free body diagram of this wooden block, assuming that this to be our system. So this is our system now. Its weight is acting downwards, mass of wood into g. There is buoyant force upwards, Fb. And then there is tension. To find out the direction of this tension, if this string isn't there, then this wood will go up. So this string is pulling this wooden block downwards. So it's a pull force, and let's say the tension is T. Now we can balance out all the forces. So if we balance out all the forces, Fb, upward force, will be equal to mg plus T, which are the downward forces. Buoyant force will be equal to weight of the liquid displaced, so rho of water into volume into g will be equal to rho of wood into volume into g plus tension T. Tension will be equal to, again if I take Vg common, rho water minus rho wood. V is 1, G is 10, rho of water is 1000 minus rho of wood is 800, which gives me the tension equals 200 into 10, so 2000 Newton, and this will be our final answer.